Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on the properties of ferroelectric ceramics under the broad subject of ferroelectric, piezoelectric and pyroelectric ceramics. We have already considered some of the properties, some of the crystal structures of the perovskites, and let us continue with that discussion. To start with today, we will look at few of the important perovskite ferroelectrics. Perovskite is a family of compounds having a particular crystal structure, and we have a huge number of compounds available in that group. However, all of them are not industrially important or technically not so important. Some of the perovskites which are very important from the application point of view are listed here. Barium titanate we have discussed, that is the most important member of the perovskite family. However, it is not the pure barium titanate always used. As I mentioned in the last lecture, that many of the capacitor materials or the dielectric materials are based on barium titanate, but many different additives are always added to stabilize the capacitance value or enhance the capacitance value, and to reduce the temperature dependence of the dielectric constant, particularly near and slightly above the room temperature. So, many different compositions are available. Sometimes they go into solid solution with barium titanate, either substituting barium site or titanium site, or sometimes they remain as a second phase material. So, we have a huge family of dielectrics based on barium titanate and barium titanate based compositions. I am not going to the details of that, but there are many standards, industrial standards available depending on what kind of dielectric somebody needs, what kind of specifications are required for a specific device, and so on. One important compound basic mention may be made about the barium strontium titanate. Here it is a barium barium site has been substituted partly by strontium. So, it is a mixed titanate of barium titanate and strontium titanate, and sometimes it is referred to as BST. This is a very important compound once again from the dielectric point of view and stable dielectric behavior. These are used primarily in the thin film form, and this is another very important group of material compound which is used in this category of ferroelectric materials. Then there is another group of materials which is called niabates. Instead of titanates, one can have niabates like potassium niobate or lithium niobate. Of course, there are also tantalates. Titanium can be replaced by tantalum, but in this case you should notice the composition. It is again a AbO3 type of compound, the perovskite family of compound. In the perovskites, actually A is normally divalent and B is tetravalent. However, in this niobates it is actually A site is monovalent, whereas B site is pentavalent. So, 1 plus 6 1 plus 5 is 6. There also in the normal perovskites 2 plus 4 is equal to 6. So, instead of 2 divalent and tetravalent, they have been replaced by monovalent and pentavalent, and that is how the charge neutrality is maintained. and so this family also has certain interesting property, and they have been used in different kind of optoelectronic devices and so on. So, that is another group of perovskites with different compositions, with deviated composition, and they are also very important from practical point of view. Then you have another mixed titanate. It is lead zirconate and lead titanate, solid solution of lead zirconate and lead titanate, normally known as PZT, which is a very important group, just like barium titanate. Next to barium titanate, PZT is another very important material used in industry. However, it is not so much used as a capacitor material. It is used in some cases, but to a limited extent, whereas its main application is in the piezoelectric range. We will be discussing in a few minutes what is piezoelectricity and what are their characteristics and what they are used for. So, we will discuss PZT, lead zirconate titanate, in that context in more details. Next we have lead strontium titanate. So, that is also known as PST. It is again a solid solution of lead titanate and strontium titanate, and that also is a useful material for some of the applications, more or less in the same purpose, but the properties are slightly different. The specifications of the devices will have to be different. Then you have lead calcium titanate, that is also in short it is PCT, that is also used as a dielectric material, and again in specific devices this can also be used in that form. The last group in this series is actually what we call lead magnesium niobate. In fact, the basic compound is lead magnesium niobate, whereas a solid solution is normally used with lead titanate. So, it is lead titanate and lead magnesium niobate, in short it is known as PMNPT. Now, this is a completely different group of compounds other than perovskites. They really do not belong to the perovskite family. They have a slightly different crystal structure. So, it is in fact this group of material is called relaxer ferroelectrics. It is not normal barium titanate like ferroelectrics. Their properties are also slightly different. In fact, it is a little difficult to prepare these compounds or synthesize these compounds. There is always a tendency of a different phase coming up, which is called the pyrochlore phase, and we will discuss these relaxer ferroelectric groups, which is coming up in recent times in a very important manner. We will discuss, maybe we will spend one whole lecture on relaxer ferroelectrics, how they are made, what their structures are, and what are their specific properties. In short, compared to barium titanate, the susceptibility peak or the dielectric peak of barium titanate is a little different. It is a little broad peak, and it also depends on the frequency. So, it is frequency dependent peak. So, the mechanisms are slightly different, and it has a much broader peak. So, it is there is a instead of a single relaxation time, there is a spectrum of relaxation times, and that as a result you have a much broader peak in this group of compounds. Of course, it has a very important property in addition to the dielectric behavior. Some theoretical understanding of this phenomena is important, or what kind of ferroelectric transition is taking place in this kind of material, that is also of a lot of theoretical interest. But in addition, there is one important property, what is called the electrostriction. So, these are mostly used as electrostrictive materials. We will discuss what is electrostrictive or electrostrictive property. Is little similar. There is some analogy with the piezoelectric behavior or piezoelectric behavior of PZT, but it is little different than piezoelectricity. So, we will discuss these properties and the crystal structures and the various different compositions of these group of materials as relaxer ferroelectrics may be at a later class. With this we go to the other important aspect of perovskite materials, that is what are the different properties. We have already discussed most of them, but this is just a consolidated picture of what are the most important properties we exploit in different ferroelectric devices or the dielectric devices. They have, we know, we have discussed several times that they have a spontaneous polarization in the absence of applied electric field. So, that comes from the particular crystal structure, particular deviation from the symmetry. So, they have their spontaneous polarization, which leads to domain structure and that also leads to dielectric or ferroelectric hysteresis. Then they have a extremely high dielectric constants. All the ferroelectric material, that is one of their major characteristics, they have a very high dielectric constant compared to any other linear dielectrics. They have a very high dielectric constant and one can make use of them for miniaturization purposes, so that a capacitor can be very thin and tiny. The dielectric constant here, of course, it has been listed as 500 to 15,000, but under certain circumstances it can be further increased to 30,000, 40,000, and in very special circumstances it can be go up to more than 50,000. However, higher is the dielectric constant, normally higher is the loss also. So, it depends on which particular property you want to exploit in a device, whether it is the high dielectric constant or a low loss. If it is a low loss, normally the dielectric constants are little low, whereas if you want to go for a high dielectric constant material, you have to accept that the tan delta value may little be high, so that a loss is also loss of, there may be a loss of energy, there may be some amount of heating and so on. There is, of course, we have already discussed the strong linear dielectric response to an applied field. So, non-linear dielectric response is also sometimes used in some of the devices. So, these are basic characteristics of ferroelectric of our interest. There are many other aspects which may not be of that much interest so far as the application potentialities are concerned. We have then few typical applications, some of them we have discussed in passing. For example, a very important application is DRAM, dynamic random access memory, that is the non-volatile memory used in extensively in the microelectronics or computer technology and so on. So, control circuits and so on. So, non-volatile memory is another application. Basically, it is a capacitor, charging and discharging of a capacitor corresponds to 0 and 1 state. So, it gives you the binary code. So, by charging and discharging you get these two codes. So, there is a large number of array of such capacitors, very tiny capacitors, not discrete capacitors, they are all array of capacitors fabricated on site, okay, or on the chip itself. So, that is the reason we get even the such a tiny your pen drives and so on, and day by day as you can see the pen drives are decreasing. That means the capacitance, the volume of each capacitance is going down every day. So, from DRAM, which was used primarily not the linear dielectrics, we have graduated or upgraded to FERAM, the ferroelectric random access memory, because it has a much higher dielectric constant. So, the miniaturization is much more efficient with FERAM. Okay. So, the current technology is basically FERAM and not the DRAM. Then you have in fact these FERAMs are already the particular compound, but who is extensively used for this is actually BST, not pure barium titanate, is BST, barium strontium titanate, and that is the material which is extensively being used. for DRAM for many different purposes, because there are not only the dielectric property when you are making a device or designing a device, not only the dielectric property, there are many other aspects have to be considered, its stability, its cyclability, its aging characteristics, and many others, okay, and how it is compatible with the rest of the materials like the electrodes, the silicon chips, and so on. So, taking all these properties into consideration, although the prime property is dielectric constant, but many other physical and chemical properties are also have to be considered once you need to design a particular device for certain applications. So, we are not going to those details at this point of time, but just not the dielectric constant, and that is the reason not the barium titanate, it has gone to the barium strontium titanate, a solid solution of barium titanium and strontium titanate. So, it is not the dielectric constant alone, the tan delta value is also of very important consideration. So, we go to the next group of applications, the different type of capacitors. Well, FERAM is also one kind of a capacitor, but it is a integrated capacitor in the form of an array, large number of arrays, whereas discrete capacitors also there. These capacitors primarily refer to the multilayer capacitors, the chip capacitors. We call it multilayer capacitors, also has another name, that is the chip capacitors. Tunable microwave devices, this is also another device made of these dielectrics. Optical waveguides, transparent materials. Many of these ceramics can be made into transparent form or single crystal form, particularly lithium niobate and potassium niobate, that kind of crystals. One can grow transparent crystals and can use as optical waveguides. Piezoelectric sensors and actuators, particularly in MEMS kind of technology, it is called the micro electromechanical systems. It is very similar to VLSI technology, but it is not that miniaturized. So, there are many miniaturized systems in the MEMS area is also available. So, both sensors and actuators, of course, we will find later on that piezoelectricity as well as the ferroelectricity, they are very interrelated. So, barium titanate, for example, is also a piezoelectric material, and they can also be used, but their piezoelectricity coupling coefficient and the actual value of the coefficients may be slightly different, but otherwise barium titanate is also a good piezoelectric material. So, one can make different kind of sensors and actuators made out of these materials, but we will see later on that the most utilized or most important compound which is used as a piezoelectric material is basically PZT or lead titanate zirconate. We have other property the similar in the same group of materials, that is what we call pyroelectric materials. We will also discuss very briefly what is pyroelectricity and what it is used for. So, there are pyroelectric detectors and sensors in the same group of ferroelectric ceramics. So, some of the ferroelectric ceramics has a very good pyroelectric property. What is that? We will discuss later. So, that more or less completes our discussion on ferroelectric materials for the time being. We have left with only one group of material, that is relaxer ferroelectrics. We will discuss that at a later class, but now we will go to change over to our discussion to piezoelectric and pyroelectric ceramics. That is also a very important electroceramics group of materials, and let us try to understand what is piezoelectricity and what is pyroelectric ceramics. Well, to introduce the subject of piezoelectricity, a piezoelectric material develops voltage upon the application of a stress and develops strain when an electric field is applied. So, this is a material, this is a group of material where there is a correlation between mechanical stress and polarization or electric field, and electric field produces strain, that is deformation, and when the crystals or the materials are deformed mechanically or stressed mechanically. So, that mechanical stress generates polarization and consequent voltage. So, one can really generate a voltage by applying a strain. So, this is a very interesting group of materials where you can convert one form of energy into another. A mechanical energy can be converted into electrical energy, or the electrical energy can be converted into mechanical energy. So, it actually acts as a good transducer material. So, using that transducer effect, one can have both kind of things. One can sense some form of parameter, and also one can actuate because there is a mechanical deformation, so there is a volume change or the geometric change, and that geometric change can be utilized to make a movement, physical movement. This group of material or this particular property was discovered way back in 1880s by once again Jackson Pierre Curie during studies into the effect of pressure on the generation of electrical charge by crystals. So, that time it was primarily not the synthetic materials, but primarily natural materials, and quartz was one of the very important piezoelectric or piezoelectric material which was available in nature, and that was being studied, and that has been studied. In fact, even today quartz has been one of the most produced in very large quantities, and it is used as electronic devices primarily for frequency generation. In fact, most of our electronic instrument today has quartz based frequency generator, whether it is a quartz clock or computer, or every system today have a frequency generator for time counting. We have then the phenomena of spontaneous polarization. Once again we have a spontaneous polarization in this case, and to generate a voltage due to changes in temperature leads to pyroelectricity. Okay, not the piezoelectric property. Another consequence of the spontaneous polarization coming up, where one can generate voltage by changing the temperature. So, in the previous case, the piezoelectric property you have, or piezoelectric material, you are generating a voltage by mechanical stress. In a pyroelectricity, once again one can develop a voltage by changing temperature. So, of course, it is little different from so called the thermoelectric effect. It is not exactly the thermoelectric effect, it is different because the origin of the two phenomena are different. Okay. So, pyroelectricity is different from so called thermoelectricity. Well, how we can demonstrate what is the piezoelectric effect? In this diagram one can see this is a piezoelectric material. To start with, there is no voltage, no pressure. Okay. So, the P polarization is 0. Then if we apply a compressive stress here from the two sides, there is a deformation, very minute deformation of the crystal or the material, and that deformation sets up a polarization, dielectric polarization here. Okay. So, by deforming you can actually generate a dielectric polarization, and you consequently you get a voltage there. Okay. So, that is the difference between normal dielectrics and piezoelectric. This is also a dielectric material, but of a different nature. This also has a spontaneous polarization. Only thing, the deformation or they are sensitive, much more sensitive to mechanical stress. So, by applying a mechanical stress, you actually polarize it, and that polarization comes up in the form of a voltage. The reverse is also true. This is the reverse, that means you apply electric field and make the changes in dimension. Okay. One has to understand in which dimension, which direction it will change, and we will discuss them in a little while. So, depending on the application of the voltage, either it will compress or it will expand, okay, and expand in different directions or changes dimensions in different directions. Okay. So, that all we have to understand. So, there are two different processes basically, one is the reverse of the other. So, this is what we call the direct piezoelectric effect, and this is what we call the converse piezoelectric effect. Okay. Is the reverse of the piezoelectric, direct piezoelectric effect. In one case we are applying mechanical stress to polarize or generate voltage, in other case we are applying voltage to generate a mechanical stress and strain as well. Now, in all piezoelectric material, you have a process called poling, okay, because we will come back, let us go to the next slide. This is what we mean by basically poling. Piezoelectric materials are also characterized by their presence of spontaneous polarization. So, just like ferroelectric material, you have spontaneous polarization, permanent dipole moments within the solid, and initially they are in random in nature. If you do not apply electric field, they are quite random in nature, they are oriented in all possible directions, so that the net dipole moment is 0. However, when we apply electric field, they get aligned. Okay. So, all of them they get aligned in a particular direction depending on the application direction of the applied field. So, in this case the direction of the applied field is here, this is, and all the dipole moments or the dipoles are aligned parallelly to that, and positive charge pointing to the top. Okay. So, this depends on the direction of the application of the field. So, all the positive charges are actually directed towards the negative charge, the applied negative charge of the negative electrode of the applied voltage. However, if you remove the applied voltage, then there will be little bit of readjustment, there is slight misalignment, but it still remain more or less aligned. Now, that depends on the what is the actually the remnant polarization. If the remnant polarization is very high, then this will retain. If the remnant polarization, value of the remnant polarization is not that high, then it may change over to its original position very quickly. So, in piezoelectric materials, mostly the remnant polarization is quite high, and therefore, even after the removal of the applied field, the dipoles tend to remain oriented in the direction of the applied field which was applied for the poling. So, the process of poling is a very important step in fabrication or preparing a piezoelectric material for device making, or to see the effect of different parameters like pressure and so on. So, all piezoelectric materials are actually poled before it is actually used in a device. So, this is what we call the poling, and normally all piezoelectric material, just like ferroelectric material, have a QD point or the QD temperature above which the piezoelectricity is lost. It change over to a paraelectric situation. So, there is no permanent dipole moment anymore. So, before the poling is normally done slightly below the Curie temperature, where the movement of the dipoles becomes easier. So, there the kinetics of the process is faster close to the Curie point. So, poling is normally done in a warm environment, normally in a liquid oil. So, close to the Curie temperature, and then apply a relatively high voltage for a long enough time, so that you allow sufficient time for the dipoles to align themselves with the direction of the applied field. So, that is the process of poling, which is very regularly has to be made for any kind of piezoelectric materials or piezoelectric ceramics. Going back to that earlier slide, sorry, in this we are coming back to this discussion. So, here we have already poled the material, and this is the direction of poling, and as a result of poling you have already the disc after polarization, that is the after poling, that means after polarization all the dipoles have been aligned in a particular direction. So, one can identify which particular side or which particular face of this material is positively charged and which one is the negatively charged. So, after poling it is no longer a completely neutral material, because the domains are not completely random. So, it has been already aligned, and therefore, there will be a positive surface and a negative surface. So, this was not there before poling. Before poling there is no surface is positive or no surface is negative, but after poling this changes has taken place. So, if now we apply a mechanical stress, we can identify which particular surface will generate a positive voltage, positive plate or the positive electrode of the voltage, and the other is the negative. So, if this is the poling direction, positive is in the top and negative in the bottom, and you try to compress, one tries to compress that material along the axis of the poling. This is the poling axis. So, along the axis, then you generate a negative charge on the positive side and a positive charge or a positive pole on the negative side. So, the disc compressed generate a voltage and has same polarity as the poling voltage. Okay. So, this is how it is, because it has become positive because a negative voltage was originally applied, and that is why it has become a positive charge. Okay. So, the same voltage will be applied in this manner. So, that is how one determines the direction of the voltage generated. If you reverse it, if you now put in tension, then a reverse voltage will generate. So, this becomes positive and this becomes negative. Now, in addition to that, one has to also notice when you compress it, it is not only changing its dimension along this axis, but it is also changing its dimension in the orthogonal direction or the right angle to that, and that is basic because of the Poisson's effect, because if you compress on this side, that is basically because of the mechanical deformation. So, in any mechanical deformation you will have a Poisson's effect. So, when you compress it, the diameter will increase. That is what has happened here. So, that is also, that means a stress is, you are applying a stress in this poling direction, but there is a component of stress in the orthogonal direction as well, and that is making it to increase its dimension. And in a similar manner, if you put in tensile load, there will be a reduction in the dimension. that is again because of the same reason. So, the dimensions are changing not only in the direction in the field direction of the application of the mechanical stress or the normal stress we call it, but also in the orthogonal directions or the perpendicular directions. So, that is also an important complication impact one has to consider when we are applying this kind of phenomena. This is the reverse of this what has been described here. We are basically applying a voltage and generating a mechanical deformation. The same thing happens here also. We are applying a voltage along the direction of the Pauling direction, and then depending on the direction of the or the charge developed within the material and the kind of polarity of the field, either you get a compression or you get a in this case it is a tension, and in this case it is a compression. Now, these two together is called motor action, because in a motor you are applying electrical field, or in fact electrical energy is converted to a mechanical energy, that is the function of a motor, electrical motor. And so, here this is also called the motor action, because application of electrical field is converted to a mechanical energy. So, electrical energy is converted to a mechanical energy, and that is why it is a motor action, whereas this is a generator action, the reverse of the motor, where mechanical energy is converted into electrical energy. So, these are the phenomena of piezoelectricity, because there are two energies are coupled together and one is getting converted to the other through a transducer effect. So, that is the main criteria of a piezoelectric effect. Now, this is I have already discussed, this is the Pauling of piezoelectric ceramics, and that has a bearing on the what kind of transducer effect you will get in the material. Well, piezoelectricity is related also to crystal structure, just like ferroelectricity was related to the crystal structure of the material. Piezoelectricity is also closely connected to the what kind of symmetry a particular structure has, particular crystal structure has. So, there is always a relationship between the crystal structure and physical properties, particularly in these group of materials. So, let us try to, we have discussed briefly while we were discussing the crystal structures the symmetry elements in a crystal, right. There are various symmetry elements, in fact there are different point groups, and these symmetries comes from the group theory. So, the elements of symmetry that are utilized we have not discussed in very great details, but one can remember this few points. The elements of symmetry that are utilized by the crystallographers to define symmetry about a point in a space. For example, the central point of the unit cell, we have discussed the unit cell. So, we can find out the symmetry elements in those geometric configurations. There are 4 different ways one can describe the symmetry elements. One is the center of symmetry. For example, in a cube, center of the cube is actually a center of symmetry. So, around that center, around that point, all are symmetric in a diagonally opposite directions. Okay. So, that is why it is called center of symmetry. You can also have a axis of rotation, that is also a symmetry element. That means, if you have an axis, then if you rotate it, it comes to its original position, and you cannot kind of indistinguishable positions. So, an axis can also be a line actually, either a vertical line or a horizontal line or a diagonal line. They may also act as a axis of rotation, that is also a symmetric element, symmetry element for the consideration of the point group of symmetries in the point groups. Then you can also have a mirror planes looking at or coming back to axis of rotation, the diagonal of a cube, the body diagonal, what we call a body diagonal of a cube is an axis of rotation, right. A vertical plane, a vertical line through the center of the faces, both the bottom face and the top face. If you will draw a line, vertical line, that also acts as a axis of rotation, because you can rotate the cube around that axis at least by 90 degrees and come back to the same configuration. So, these are actually 4-fold rotation, 3-fold rotation, 2-fold rotation axis and so on. Then you have another symmetry element is mirror plane. You can consider a plane through the geometry or through the volume of the unit cell, and you can see the one half is a mirror image on the other half. So, that is also one can have a symmetry, that there is some symmetry available along across a mirror or across a plane. And sometimes there are a combination of these, okay. Either a center of symmetry is combined with the axis of symmetry, or a mirror plane is combined with axis of rotation, and so that also give rise to different other symmetry operations. Okay. So, considering all these kind of symmetries of a point group, we have 32 different classes. All the possible geometries will have 32 different classes or the point groups. Okay. So, within that all the kind of geometries or the geometric configurations can be classified or grouped together. So, in crystallography we will always consider 32 crystal classes, and we have also discussed briefly during a discussion on crystal structure. These 32 point groups have been subdivisions of 4 basic crystal systems. Okay. So, there are and then we have Bravais lattices and so on. So, there are basically 7 crystal systems. So, one should distinguish between 32 crystal classes and crystal systems. These are the basic difference between crystal classes and crystal groups. Some of these crystal classes are grouped under different crystal systems. So, we have 7 different crystal systems, and they are quite familiar names to us by now. These are triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, or sometimes called trigonal, hexagonal and cubic. Their symmetries are different, as you may imagine that cubic is the most symmetric, okay, whereas triclinic is the most non-symmetric. So, this is how the order changes, and there will be some kind of, we have seen in case of particularly barium titanate, then there are 4 different polymorphs like cubic, tetragonal, orthorhombic and rhombohedral. Okay. So, these are different kind of symmetries, and they can different kind of distortions. So, they have different level of symmetries. Okay. Now, of the 32 point groups or crystal classes, it is the same thing. Sometimes they are referred to as point groups, or sometimes the crystallographers primarily call them crystal classes. 21 crystal classes do not possess the center of symmetry. One of the operations of the finding out this symmetry of a geometry is the center of symmetry. Okay, is one of the 4, and it has been found, or one can visualize, one can find out from different ways it has been, the crystal classes have been generated. Out of the 32 crystal classes, 21 do not possess a center of symmetry. a necessary condition for the piezoelectricity to exist, and 20 of these are actually piezoelectric. Okay. That is a very important statement. For piezoelectricity to occur in a material, the crystal or the crystal structure must have certain conditions, and that is it must not have a center of symmetry. Okay. So, any crystal class or any crystal structure having a center of symmetry will not be having piezoelectric property, and that is a very important statement, and it has to be remembered all the time. Okay. So, out of 32 point groups or crystal classes, 21 do not possess center of symmetry, and they are the materials, they are the crystals in which piezoelectricity can be observed. However, out of 21, one does not have, although it does not have a center of symmetry, but it also does not have a piezoelectricity, but for a slightly different reason. One class, it has been mentioned in the next line, one class although lacking a center of symmetry is not piezoelectric because of other combined symmetry elements. Okay. So, 20 crystal classes do not possess the center of symmetry, and all of them, any material crystallizing in this particular crystal structures or crystal classes will have piezoelectric property. Well, their effect may be small or big or large, but in principle they have the piezoelectric property in them. So, there are a large number of, so its impact as you can see, out of 32, 20 have the piezoelectric property. So, piezoelectric property is basically a common property of many minerals and crystals and so on. Okay. So, only 12 crystal classes do not have that, but otherwise 20 of them have the piezoelectric property. So, in principle many materials do have piezoelectric property. Well, this can be summarized in this form of a flow diagram. 32 crystal classes has been subdivided into two groups. One is non-centrosymmetric, 21 of them, and another group is centrosymmetric, so 11 of them. So, these 11 do not have piezoelectric property. Okay. Now, so out of 21, 20 has the piezoelectric property, as already mentioned. One for some other consideration it does not show piezoelectricity. Out of this 20, 10 are pyroelectric. Okay. All of them, piezoelectric, pyroelectric and ferroelectric, has certain commonality. Okay. They have all of them have a spontaneous polarization. That means they have some kind of a internal or geometric deformation in the crystal structure, and that leads to the dipole moments. So, the dipole moments are already there. So, the out of the 20 different classes of piezoelectric material, 10 are pyroelectric, okay. And then out of these 10, some are ferroelectric. Not number is exactly not known, it cannot be identified very clearly, but some are ferroelectric. Okay. So, from this it is one important aspect you have to remember, all ferroelectric materials are pyroelectric and also piezoelectric or piezoelectric. Okay. So, any ferroelectric material are supposed to have the pyroelectric property as well as piezoelectric property. However, all piezoelectric materials need not be ferroelectric. Some of them are and some of them are not. For example, quartz. Quartz is a very important piezoelectric material, extensively used in industry, for particularly electronics industry, but it is not a ferroelectric. So, similarly, all pyroelectric materials are all ferroelectric materials are pyroelectric, but all pyroelectric materials are not ferroelectric. So, that is the kind of interrelationship between them. So, it all depends on what kind of crystal class it belongs to. Okay. So, the materials, the crystal class of the material is very important, whether we can get some piezoelectricity, pyroelectricity or ferroelectricity. So, that is the classification one can have. Well, there are some characteristics of the piezoelectric effect, some of which we have already discussed. As in ferroelectricity, above a critical temperature. So, there is also a critical temperature called the Curie temperature. So, each perovskite crystals exhibit a simple cubic symmetry and no dipole moment. Okay. Now, one has to find out there is always a phase transformation associated with this Curie temperature. That means, the Curie temperature and the phase transition more or less occur in the same temperature, although they have a slightly different origin. Okay. They are not exactly the same all the time, but they are very close. So, above the Curie temperature there is a cubic symmetry, and cubic symmetry means there is no dipole moment, permanent dipole moment. So, just like ferroelectricity is lost beyond the Curie temperature, piezoelectricity is also lost beyond the Curie temperature. So, one can once again identify a critical temperature called the Curie temperature. At temperatures below the critical temperature, that is the Curie temperature, however, each crystal has tetragonal or rhombohedral symmetry and a spontaneous dipole moment. So, it is very similar to the ferroelectric domain, ferroelectric materials we have discussed earlier. Adjoining dipoles, once again we have domains, just like ferroelectric domains, we have a ferroelectric domains in piezoelectric materials as well. So, adjoining dipoles form regions of local alignment called domains. The alignment gives a net dipole moment to the domain, but thus a net polarization. So, each domain has a net polarization, but when it associated with neighboring domains which may be at a different orientation. So, they cancel each other, and therefore, there is no net polarization when the average is taken over a large number of domains. There are few more characteristics one can visualize. The domains in a ceramic elements are aligned by exposing the element to a strong direct electric field, usually at a temperature slightly below the Curie temperature. That is the phenomena of poling. Okay. So, the domains can be aligned externally and through a process of poling. Through this polarizing treatment, that is the poling treatment, domains most nearly aligned with the electric field and expand at the expense of the domains. The domains more nearly aligned to the electric field expand, that was also discussed during ferroelectric domains. So, which are little favorably oriented to the direction of the application of applied field, they grow, and the domains not so favorably oriented, they actually shrink. So, the element lengthens in the direction of the field, and as a result of that there is a dimensional change also. Okay. So, this kind of poling also leads to some amount of dimensional change, although minor. When the electric field is removed, most of the dipoles are locked. That is what also we have discussed earlier through the illustration, that they are mostly locked because the remnant polarization is very high, and therefore, you have I am sorry, one thing you must, it is not the remnant polarization alone, it is actually the coercive field. So, it needs high coercive field also to randomize them. So, both the remnant polarization is high as well as the coercive field is also quite high, and therefore, one can retain the alignment. The element after poling of course has now a permanent polarization, and the remnant polarization and is permanently elongated. That is also as a result of poling you are getting the material getting polarized, and there will be consequently there will be some dimensional change. Well, we will just have a brief discussion on this. We will discuss them in details later on, but to start with we will introduce actually 4 different coefficients. One is the strain coefficients, because the 2 parameters are interconnected. One is the electric field and the mechanical strain. So, there must be some coefficient which relates both of them. So, that is the strain coefficient. It is actually Dij, it is not II, it is Dij, and it is a subscript which actually denotes the direction of the application of the field and the direction of the consequent response. Okay. So, the strain coefficient is one parameter which describes the property of the piezoelectric materials, and its unit is meter per volt. Then we have a charge output coefficient whose unit is coulomb per Newton, and that is the charge density developed coulomb per meter square per given stress. Stress is Newton per meter square. So, it becomes coulomb per Newton. So, how much charge is actually generated, and how at what kind of force you are applying. So, voltage coefficients are the field output coefficients. These are denoted by Gij again, it is not II, Gij. So, the open circuit electric field developed per applied mechanical stress. Once again it is very simple. We have applying a mechanical stress and electric field is generated. So, there must be a coefficient, there must be a relationship between the mathematical relationship between the two, and the coefficient is Gii, and the unit is volt per meter. Applied mechanical stress is Newton per meter square. And finally, and very important parameter, because it is a transducer, one kind of energy is getting converted into another kind of energy. So, there is a coupling coefficient. So, it is basically a ratio, there is no dimension. So, it is this coupling coefficient is the energy ratio describing the conversion from mechanical to electrical or vice versa. And of course, K is the coupling coefficient, and K square is actually the ratio of energy stored mechanical or electrical to the energy generated or applied, okay. Not generated, applied. So, it is the ratio of how much energy is getting generated. One form you are applying one form of energy and getting back another form of energy. So, there must be a certain amount of loss, and so the coupling coefficient basically is the ratio of the two energies, and therefore a number. So, K square actually output of mechanical energy, input electrical energy, or output electrical energy, input mechanical energy. So, these are the 4 terms by which the property of piezoelectric materials can be described. So, we complete this discussion for the time being. We will continue our discussion in the next class for the other coefficients and how we can generate different coefficients, what their significance. We will take it up in the next class. Thank you very much.